stopped, so can begin. I have the pleasure this afternoon bringing in Tim Lichtenberg. He works in a unique space at the interface between astronomy and geosciences, where he gets to help bring understanding to the evolution, not only of solar system formation and planets, but also how life is interconnected with the evolution of planets. It seems he's found exoplanets early on during his Bachelor's of Science at the University of Groningen. His thesis was constraining exoplanet characteristics with astroseismology, so creating precise characteristics of their mass and radii of exoplanets using a couple different methods. For his master's, which was in physics, he modeled gravitational instabilities in compact and massive protoplanetary disks with adaptive mesh refinement techniques. This was also at the University of Groningen, graduated in 2014. This brought a new way of modeling gravitational instabilities from a two-dimensional characterization to a 3D adaptive mesh refinement. For his PhD in science, he had twin advisors, Teres Gura and Michael Meyer, where he undertook the research of thermal evolution forming planets, including isotope enrichment, differentiation, and volatile retention. And this thesis actually won a prize from the International Astronomical Union and German Astronomical Society. Since graduating, he moved on to the University of Oxford, where he held a Swiss National Science Foundation for Early Postdoc Mobility Fellow from 2018 to 2019. And then from 2019 on, he's been the Simons Collaboration on Origins for Life postdoctoral fellow, also at the University of Oxford, where he's currently investigating the growth and early atmospheres and surface conditions of rocky planets. He's an associate member of the NASA research program Alien Earths, and he's a co-lead of the Exoplanet Science Working Group of the Large Interferometer for Exoplanets, or LIFE collaboration, which I hope gets built up on the moon in the coming decades. So with that, I give you Tim, who will be speaking today on geophysical evolution during rocky planet formation. Take it away, Tim.
Thank you so much. Thank you. Yeah, thank you everyone for being here. Can you see? You should be able to see my screen, and I hope this time it works with the advancement of the slides. We'll see about this. So if you have a question during my talk, please just put it maybe in the chat. I'll try to monitor the chat. And yeah, anything else, of course, happy to answer after as well. So right. Yeah, okay. So I model specifically the geophysical evolution of rocky planets, and I try to understand their early life birth cycles, how they form, accrete, and what physics and chemistry basically do to them in their forming atmospheres. And the ultimate goal of this is to understand the limits of potentially habitable planetary environments. And in this talk here specifically, I actually want to talk about some characteristics, some key characteristics that may distinguish the solar system from exoplanetary systems. And that starts during the accretion phase, the protoplanetary disk phase already. So I'll start with that and explain some of the key characters, try to explain some of the key characteristics of the solar system, how they're inherited from accretion, and then extrapolate those aspects and characteristics and mechanisms that shaped the solar system to extrasolar planetary systems, and say something how we can test those mechanisms across the exoplanetary census. Okay, so to start with that, what you see here is a diagram or an illustration, like you've seen probably many already, just showing actually the general structure of the solar system. Until about 25 years ago, a little bit more already by now, this was really the only planetary system we knew, right? And in a historic perspective, this is really like a perspective shifting development in the field, because all our theories, all our physical and chemical theories, were primed to reproduce and explain exactly this structure. And I emphasize this so much because we come back to this later. What are the typical processes that potentially have produced this structure? So this is with the terrestrial planets here in the inside that are mostly dry and small compared to the outer solar system with much more massive planets, gas-rich and volatile-rich planets. So this is the structure we knew about. But of course, in the last few years, specifically actually during the last 10 years, our horizon has significantly expanded. And now we can compare just the uniqueness of our own solar system and start to compare it with characteristics, for instance, dynamical and orbital characteristics of other planetary systems, but also increasingly composition-related aspects. This is what I want to outline here in this this diagram. This is a mass radius diagram. So here's planetary mass and Earth masses. This is planetary radius and Earth radii. This plot is from 2017, but it hasn't populated much more recently in the last few years in this lower corner, which I want to focus today. So the dots you see are measured exoplanets with the uncertainties in mass and radius that we know about. They are color-coded with the equilibrium temperature. And the different lines you see here are isolines of specific composition. So for instance, if you go up here, then these planets are more composed likely of light elements, light element contents. If you are somewhere down here, then they are probably composed of more denser elements like iron or metal. Now, if you're somewhere more in the middle of the diagram, close to this 100% H2O line, then at least theoretically it's conceivable that planets form that are composed of a majority of water. So this is a potential structure for such a planet is here shown on the right-hand side. This, at the first sight, this seems rather unlikely that you would form a planet, Earth mass planet, with a, let's say, I don't know, 38% of water or so. But then actually, if we look across the solar system, we look at planetary objects like Ganymede, for instance, then we see this is actually not just theory, but it's actually fulfilled already in our own solar system. Also, comets, for instance, have a very large water ice component that, if you would pack them and make a planet just purely out of comets, like Pluto, for instance, then it would be composed very dominantly of volatile ices. Now, the question then really becomes, what are the limits to really maintain an Earth-like planetary mixture? How far can you deviate from the rocky composition that we see in the terrestrial planets to really count still as an Earth-like planet, given the apparent spread in composition that we observe in the currently known exoplanet data? To illustrate you how problematic this is and how easily we may cross those boundaries, this right-hand illustration here shows the difference between an Earth-like world with about 0.1 weight% of water in its interior and its whole bulk budget versus an icy world. So if you take the Earth and you would mix into that composition just about 1 weight% of water, then the whole planet would feature a global ocean, and the high pressures at the base of this global ocean would be so high that actually water wouldn't be in a liquid state anymore, but rather it would be in high pressure ice phase, such that any interaction between the planetary mantle here and the atmosphere, if there would be one, would be inhibited or be completely shut off. And this is dramatic for the limits of habitable environments, because on Earth at least, we believe that cycling, geochemical cycling between the mantle and the atmospheres over a billion-year timescales actually acted as a sort of thermostat that kept the surface temperature in a range that is amenable for life as we know it. Now, so far, this seems all like a lot of theory, But in order to show you that this is exactly the discussion that we have in the exoplanet community, this plot here shows you the water mass fraction of the so-called TRAPPIST-1 system, which is a famous planetary system that features several Earth mass planets, some of which are also in the so-called liquid water habitable zone of their star. So this is a very small star. It's an M dwarf, one of the smallest M dwarf stars we know about in the solar neighborhood. And what you see here, these dots, are the inferred water mass fractions of these planets. So this is the semi-major axis of each of these planets. And here's a planet, here's a planet, here's a planet, here's a planet, and so on. And the different colors are the assumed iron mass fraction. So we know very little about these planets, but we know their masses and their radii. And so this gives you an indication of their densities. And so if you assume an iron mass fraction, for instance, like the one of the Earth, which is on the order of 32 weight%, then this gives you an indication of the water ice contribution that is necessary to explain the density. For these outermost planets, this seems as if it would require a substantial water ice fraction or as part of their bulk mass, up to a few weight%, perhaps even 10 weight%, putting these planets firmly in this regime. Okay, so this means maybe planetary formation and evolution can generate a large flurry of potential pathways of evolution and create planets that look and behave very differently from the terrestrial planets that we know in the solar system. And what I want to highlight, what I want to emphasize now is that in the last 5 to 10 years specifically, there has been a very rapid development of very crucial new constraints that tell us something about the timescales and timescales of processes that shape the bulk composition and ultimately the climate states of these worlds. The first one I want to highlight is that we have now evidence for substantial temporal fragmentation of the planet formation process. So what do I mean with this? This is illustrated here on the left hand, on both of these sides, on the left and right hand side. We have evidence from both exoplanetary systems and from the solar system that planetary formation commenced immediately together with a protostar. So basically, contrary to the old picture, where you thought of, the star, a protostar forms, a protoplanetary disk forms, and then over millions of years, the planets around that star formed, we now have evidence that the planetary formation process starts contemporaneously with the star formation process itself. For exoplanet systems, the evidence looks like this here on the left-hand side. So what you see in y-axis is the mass in solids, in either planetary disks, protoplanetary disks, or in extrasolar planets. The x-axis is not so important for the point I want to make. This is the stellar mass. And these lines that you see is the integrated mass in class 0, class 1, or class 2 disks. So what are these? Class 0 and class 1 disks are basically protostars, young stellar objects that are actively accreting mass from their surrounding star-forming environment. And class 2 disks are disks that are already shut off from the ambient star-forming environment, but that have formed a million-year long-lived protoplanetary disk. And these dots here are individual exoplanets that we measure in the exoplanet census. And what you can see is the mass in class 2 disks is order of magnitudes below the masses that we observe in exoplanets. But they're supposed to form out of this dust component that is available in those disks. This tells us that planet formation really must commence and start at an earlier stage in the class 0 or class 1 disk stage. We have complementary evidence from the solar system. And you see this here on the right-hand side. This shows time after CAI formation in mega years after the formation of the solar system. This is normalized to the formation of so-called calcium-enriched inclusions, which are the oldest dated solids from within the solar system that we know about. And the y-axis for the point I want to make is not that important, but there are basically two parts, a red part and a blue part. Blue means roughly outer solar system materials, red part roughly means inner solar system materials. We see that the inner solar system materials, the points here, which are planetesimal formation ages or times after CAIs, already start in the first mega year after sea ice, which is the same time scale as the class 1 stage. And we not only now know that the planetary formation commences extremely rapidly together with the protostar itself, but we know in the solar system, in the inner solar system at least, that the timescale for finish or the cessation of accretion, specifically for the Earth, for instance, took much longer, more on the order of tens of millions of years, potentially 100 to 200 millions of years after solar system formation. Now, this is one line of evidence, but not only is planet formation temporally fragmented, it's also spatially fragmented. And again, we have evidence from both exoplanet systems and the solar system. Left-hand side here shows evidence from exoplanetary systems for spatial fragmentation of the dust component that makes exoplanets, and here these ring structures in protoplanetary disks. The right-hand side shows comparable and complementary evidence from isotopic systems in the solar system. So what you see here is what is commonly referred to as the nucleosynthetic isotope dichotomy of the solar system. And it shows you deviations in isotopes, in chromium-54, for instance, and titanium-50 relative to the Earth. You see two large clusters. The individual points here are meteorites and planetary objects, like for instance, the Earth, Moon, or Mars. You see that these red ones here, the so-called non-carbonaceous reservoir, clusters around a certain value, while the blue values, or the so-called carbonaceous CC reservoir, cluster somewhere else. And this means two things. First of all, it means that the solar system itself accreted not from a homogeneous source, but rather from material that was created in at least two different nucleosynthesis events, such as, for instance, supernovae, Wolf-Rayet stars, or neutron star mergers. Now, looking at this, we can immediately start, to think about this type of structure that actually kept the material apart from the disk and prevented homogenization in the protoplanetary disks. For instance, structure formation like these images here. Maybe this has something to do also with a different type of chemical segregation that we observe in the solar system. Namely, the difference that I mentioned at the very beginning between the dry and inner solar system, where the planets have very little water and other volatiles by mass, versus the wet and volatile-rich outer solar system, where the planetary objects feature much higher volatile components. So traditionally, this has been, of course, associated with the appearance of a so-called snow line in the protoplanetary disk. The idea here is, you have the protosun, you have your gas and dust-rich protoplanetary disk surrounding that protostar, and somewhere in the middle of the disk, at a few AU or so, there's a line, an imaginary line essentially, that divides hot parts of the disk where water is in the gas and vapor phase, and colder parts where water is actually in the solid ice phase. And then this picture and the static picture, basically the terrestrial planets accreted in the dry inner parts, while the outer solar system, the wet material, accreted beyond the snow line. Now, these various lines of evidence that I presented to you regarding temporal and spatial fragmentation, however, have highlighted in the past few years specifically actually that planet formation is not just an orbital process, but it rather actually is a very incremental growth process. And this is specifically highlighted in the growth over many orders of magnitudes in the disk. Specifically, actually, planet formation is not actually easy from a physical perspective. From a theoretical understanding that is supported by laboratory experiments, planet formation actually shouldn't happen. The reason is that when grains that are accreted onto the protoplanetary disk on the order of micrometer sizes, for instance, monomers and aggregates, they start colliding and grow to larger aggregates. But at some point, they experience a number of growth barriers, approximately around centimeter to decimeter size scales. And these growth barriers to growth are listed here below. For instance, the so-called bouncing and fragmentation barriers lead grains that are on the order of centimeter sizes, leads them to stop growing. They cannot grow anymore and rather fragment because the mutual collision velocities are too high and the material this material strength is not high enough to keep them together. Keep them together. The radio drift barrier is another one that is related to the orbital timescales of these grains. When they grow and become larger and larger, they actually interact with the surrounding hydrogen-helium disk, and this makes these grains experience a headwind from the surrounding disk. Because of that headwind, they lose angular momentum and spiral inwards onto the proto star on the timescale of a few thousand years. So much shorter timescale than the actual accretion timescale. So from this laboratory informed perspective, planet formation shouldn't happen. But it does, obviously, because we observe our own solar system planets, we stand on one, and we have all these exoplanets around. So how to solve this issue? And as a potential solution, the community has has invested a lot of time in the past 10, 15 years into this issue. And what emerged from this really is the view that actually the growth doesn't proceed linear through these growth stages and size regimes, but rather jumps over the centimeter and meters barrier, centimeter and meter scale, directly from millimeter to kilometer-sized objects, via the so-called streaming instability, which is a fluid dynamical instability, a fluid dynamical process that arises from the large-scale motion of dust particles. So in order for that to proceed, basically, you need a lot of particles locally concentrated in a very narrow area of the disk, and then the gravitational attraction of these dust grains then directly gravitationally collapse to kilometer-sized objects, directly from millimeter-sized objects to kilometer-sized objects. And this sort of changes the question, or changes the problem of planet formation from the question, how do planetesimals, the first seeds of the accretion process, form, to how does the disk locally enhance the dust-to-gas ratio in order to then trigger self-gravitation and form the first planetesimals. And from a historical perspective already, but very robustly, both theoretical experiments and related also to some observational evidence, is the view that the snow line itself actually is this location that can locally enhance the dust-to-gas ratio significantly and trigger planetesimal formation. So how does this work? You have the snow line here. This is a side view of the protoplanetary disk. Here inside, gas in the vapor state, here gas in the solid state. And then drifts, particles that are here, that are ice-rich, they are stickier than dry grains and can therefore agglomerate to larger sizes. This makes them feel a stronger headwind, they lose more angular momentum, and they drift rapidly inside toward the protostar. But when they basically drift past the snow line, the ice component sublimates, they immediately lose a lot of their mass and size, therefore they drift slower. And this leads to a sort of traffic jam at the location of the snow line that locally strongly enhances the dust-to-gas ratio and triggers the streaming instability and therefore planetesimal formation on the order of 10 to the 5 years. So this effect can be very effective, but it's rather slow. There's an additional effect operating at the snow line, which relies on the Brownian motion of particles in vapor phase, in the vapor state. So basically the gas diffuses outside, vapor, gas, water vapor from inside the snow line diffuses outward and refreezes onto grains just outside the snow line, enhancing the solid surface density and again triggering the streaming instability. This is called the cold finger effect. It's less effective, but operates much faster than the traffic jam effect. So what do these two mechanisms, these physical mechanisms, actually do on the large evolutionary, million-year-long evolutionary timescales of this? And so we asked this question 2 years ago and tried to understand if the succession of these events can explain actually some parts of the structure that we observe today in the solar system. So for that, we basically, because of the evidence for very early planetesimal planet formation, this model or this scenario already starts during the collapse of the protostar itself. You see this here. So in this model, basically, the giant molecular cloud core that ultimately forms the solar system rotates with a homogeneous rotation rate, then it collapses gravitationally and forms the protostar. Because of angular momentum conservation, then, the disk accretes and forms from the inside out, becomes larger by viscosity and further subsequent accretion. And so it starts small and becomes larger over time. Now, during this build-up phase, what happens with the snowline and the dust component? The dust grain are accreted onto the disk, they coagulate, and they drift and grow at the same time. And this leads to a succession of events that builds structures in the disk. This is shown here in this video that I will show to you now. So this is the orbital distance within the disk, and this is the time scale. And let me play this again. So here in the class 1 phase, which is when the protostar is still accreting, the snow line, which is this boundary region in the disk, drifts from the inside out because the disk is actively accreting, and viscous heating in the disk leads to an increase in the temperature in the disk during the infall phase. But then at the transition from the class 1 to the class 2 disk stage, this effect vanishes, and subsequently the disk is just heated from the irradiation of the central star. Because of the different time scales and efficiencies that I explained to you before, there are two planetesimal populations forming. This is shown in these red areas here, which is planetesimal formation rate. So basically a change in the surface density of planetesimals per time step in the simulation. So here, very early during the infall stage, the class 1 stage of the solar system, a small planetesimal population forms in the inner solar system. And then later on, while the disk is cooling and the snowline moves inwards, a large planetesimal population forms at orbital regions starting further outside. You will see this from now on in this color coding to simplify the discussion here, where this inner region is called Reservoir 1, shown in red, and Reservoir 2, the traffic jam formed population, forms later and is color coded in blue. So immediately from inspecting this visually, we can see that there are two large structures formed in the disk. And this can be related to the distinction and the deviation and anomaly we see in stable isotopes today. So I said that this isotopic anomaly we observe in the solar system is evidence for at least two nucleosynthesis events that have contributed to the disk. But it also gives evidence for physical barriers in the disk that kept the disk from not homogenizing entirely. And the reason is dust drift. This presents a problem and gives a mechanism, which is why in the first place we never actually, from an astrophysical point of view, we wouldn't expect any heterogeneity in the isotopic composition of the disk. So imagine a dust particle here, a pebble, carrying a specific isotopic information. The drift, which operates on a 1,000-year timescale, is much faster than the evolutionary timescale of the disk, which is on the order of a few million years. And so any information that is carried with these pebbles should make it to any part of the disk in time and homogenize the entire reservoir. But obviously this didn't happen. We have evidence for this. And so what we need to do is we need to find a mechanism that prevents entire homogenization of the disk. So in order to check actually in this simulation and in this scenario of disk buildup and planetesimal formation, can we preserve an initial isotopic heterogeneity in the disk? So in order to test this, we measured the so-called Pebble Flux at 2 and 15 AU. The Pebble Flux is basically the amount of mass that drifts past a specific orbit. And this is shown here on the right-hand side. You see time after CEI formation in mega years, again on the x-axis. You see the Pebble Flux in Earth masses per million years on the y-axis. And these lines here correspond to the Pebble Flux at 2 AU and blue to 15 AU. And what you see is that during the disk buildup phase, specifically at the end of the disk buildup phase, the class 1 phase, the Pebble Flux in the inner and in the outer disk is on the same order of magnitude. Basically, all the material that accretes onto the disk drifts and makes it past a specific orbit. But then, after the disk has been established in the class 2 phase, the two fluxes diverge, and there's a reservoir separation building. So why is this the case? It's very simple. The reason is that any pebble that comes from the outer solar system, accretes onto the disk in some outer parts, carries a specific isotopic signature, cannot make it into the inner solar system because it contributes to planetesimal formation in the outer solar system. The amount of mass that is built up in this outer solar system is so large that it has a significant qualitative evolution effect on the amount of dust mass that makes it, or that not makes it, into the inner solar system. So qualitatively, this looks like this here. So the initial infall while the disk is building up is enriched in supernova-derived isotopes. Then the infall itself changes in isotopic composition, becomes depleted. And while the disk is building up, basically the snow line moves outside. Once it has stabilized in the class 2 phase, the grains start their large-scale motion onto the inside, but the homogenization of the disk is stopped because of planetesimal formation at the snow line, and therefore we end up with what we're seeing today, namely a separation between the outer solar system rich in CC, what we call today the CC composition, and the inner solar system, the NC resin. Okay, so this is interesting with regards to structure formation and isotopic composition, but what does it have to do with planetary accretion processes? And it turns out that this sort of evolution has qualitative and quantitative influences on the mode of accretion that we expect for the terrestrial planets. So to test this, we basically asked the question, relative to the two currently discussed end-member cases of planetary accretion, into which one would the terrestrial planets roughly fall? And these two end-member cases are planetesimal accretion, which is by now the more classical view of planetary accretion that is inherited from the Apollo missions, basically, where you form planetesimals and then those accrete ballistically by mutual collisions to form larger embryos and ultimately planets. Pebble accretion is the more modern theory. It has historic roots going back 100 years ago, but the more modern view of this scenario is basically emerged in the last 10 years only. And in this view, basically the pebbles, the initial dust grains, accrete directly onto the protoplanet and contribute to the growth of the embryos. So what is the difference? The difference is shown here and illustrated here at the bottom. This is the protoplanet, this is a planetesimal, and if a planetesimal would enter the potential well of a protoplanet, but doesn't directly accrete on it, like via the geometric cross-section, it would be scattered, like you can see here and here. It doesn't accrete onto the protoplanet. But a pebble, on the other hand, would, by means of the headwind that it feels, the loss of angular momentum due to the interaction with the disk and the proto-atmosphere of that planet, it would continue to spiral inwards and ultimately accrete onto the protoplanet. Therefore, in certain regimes of disk evolution and pebble growth and protoplanet mass, pebble accretion can be a very efficient contributor to planetary accretion. So we measured those quantitatively in the inner disk because we were specifically interested in the growth mode of the terrestrial planets, and this is what you can see here at the bottom. So let's focus on these red lines. The y-axis shows the growth timescale, which is basically the inverse of the accretion efficiency. And the solid lines shows the growth timescale of pebbles, and the dashed lines shows the growth timescale for planetesimals. What you can see is that for these dust fluxes here at the top, the initial disk, the initial growth phase after the first planetesimals here formed in reservoir 1 is dominated by planetesimals, so collision dominated. The reason is that basically there are no pebbles in this phase. All the planetesimals are very efficiently converted to, all the pebbles are efficiently converted to planetesimals, and the initial accretion phase is dominated by mutual collisions. But then, with the establishment of the class 2 disk, actually, the growth mode changes. And that is because you see here at the top, the pebble fluxes are roughly comparable, so pebbles from the outer disk can make it inside and accrete onto the embryos that have already formed by mutual collisions. But then here, after about 2 million years, the growth mode changes again. And the reason is that this reservoir separation here at the top. The inner disk becomes starved of pebbles because pebbles from the outside never make it into the inner solar system because of that reservoir separation and planetesimal formation in the outer solar system. So what this means, again, schematically, is that initially there are no planetesimals, the disk is spreading and growing. Then we have planetesimal formation, icy planetesimal formation in the inner disk, collisional growth, migration, and pebble accretion. The same roughly happens in the outer disk, but delayed to that because the second planetesimal reservoir in the outer disk forms later, but then these succession of growth stages operate a little bit faster because the solid surface density in the pebble flux, the outer disk, is larger compared to the inner disk. Now you may have immediately spotted an issue there, which is that every planetesimal that forms in the simulation is extremely water-rich because everything forms below the snow line. Because for planetesimal formation in the streaming and stability scenario, you could require a higher solid surface density. So how the heck can this explain the solar system where we have a dry inner solar system and a wet outer solar system? And the reason in the scenario, or the explanation in the scenario, is the radiogenic decay heating by aluminum-26. So while the planets are growing, these late stages here are dominated by accretion energy, so the potential energy of accretion, which melts these protoplanets. But the initial phase, when the planetesimals are small, on the order of 100 kilometers or so, this is not dominated by potential energy, but depending on the accretion time scale, can be dominated by aluminum-26. What is aluminum-26? It's a half-life, it's a short-lived radioactive isotope with a half-life time of roughly 700,000 years, dominantly produced in supernova type 2 or in Wolf-Rayet stars. And the energy output from aluminum, the heat output that can heat the surrounding silicate materials in this time frame, is actually very strong. In the early solar system, the abundances of aluminum-26 were extremely high, and the radiogenic heat output and chondritic materials that formed the planetesimals and planets of the solar system was several orders of magnitude higher than anything that we observe today in the solar system. The heat output was so strong that it melted the first generation of planetesimals, led to very volcanically active bodies, and could lead to complete magma oceans powered by the energy output of aluminum-26 decay. Here, for instance, you see a 3D simulation of a planetesimal, Rayleigh-Taylor instabilities that are triggered by melting internal deformation of the solid state material in planetesimals. And in addition to the thermochemical evolution, this also led to chemical segregation. Chemical segregation in terms of metal silicate segregation, but also with consequences for the volatile evolution of these bodies. So on a statistical sense, this here is a phase, parameter space of formation time after CAIs for individual planetesimals. This is the planetesimal radius. The color scale shows you the highest mean temperature, the volumetric mean temperature of these planetesimals. We see that this bottom part here, the early formed bodies and large bodies that are favored by the streaming instability, they can become very hot, hotter than the silicate melting temperature. And this has implications for specifically two lines of chemical segregation that I want to discuss. One is related to water-rock interactions, hydrothermal activity, and one is related to core formation. So the segregation of metals, for instance, Fe or nickel, and the surrounding silicates. Now, if we plot those two things together, like this parameter space of planetesimal heating by aluminum-26 decay and this disk build-up scenario, then you immediately see that these early planetesimals, the reservoir 1 planetesimals, become substantially heated, while the later formed planetesimals, reservoir 2, only experience low internal processing by this decay heat. And this leads to different timescales of core formation of these planetesimals. This is shown on the left-hand side. This plots again time after sea ice. And the y-axis in this case is the fraction of the birth planetesimal population, so the volumetric fraction, volumetric percent actually. For simplicity, let us just focus on this peak here. This is the rate of core formation, the separation of metals and silicates and planetesimals over time. What you see is that there's a peak in this metal silicate segregation, so build-up of core formation in these planetary bodies at about 1 megayear here. And for reservoir 2, you see that there are peaks of core formation between approximately 2 and 4 megayears. At the top, you see the ages or the timescales of core segregation from magmatic iron meteorites that we observe and have evidence for from the hafnium-tungsten dating system. You see that the plots in reservoir 1 roughly explains, within the uncertainties of the ages, the clustering of ages in the NC reservoir, and reservoir 2 explains the clustering of the ages of cores in the outer solar system. The same goes for hydrothermal alteration or aqueous alteration in the outer solar system. So what happens if you have an initially homogeneous water-ice rock mixture? First, the water ice would melt. Then depending on the heating time scale, it could react with the ambient host rock and form phyllosilicate phases. But if the temperature becomes too high, then these phyllosilicate phases would decompose again. And parts of that would also degas then either via hydrogen or directly via other outgassing processes. Now, what happens here, so important here in this plot is this peak and this peak. In reservoir 1 actually, reservoir 1 displays a peak in hydrous rock, and the buildup of hydrous rock phases, phyllosilicates for instance, between 0.3 megayears and 1 megayears. But then actually this decreases again. The reason is that it becomes so hot in these planetesimals that no hydrous rock phases can be maintained. They would all decompose. Reservoir 2, on the other hand, builds up a peak of hydrothermal activity and hydrous rock phases between 4 to 5 megayears. This first peak can explain why there's a difference between the inner and outer solar system, namely why, despite the planetesimals accreting very water-rich, they can become dry during their internal evolution. And second, this peak here in the outer solar system explains the clustering in aqueous alteration phases that we observe in the outer solar system population. So shortly summarizing, before I come to turn this around for the last 10 minutes on the exoplanet population, this model is a physical forward model that can explain key characteristics of the solar system, including the meteoritic meteorology, and make suggestions for the mode and timescale of accretion. And it does so by using distinct bursts of planetesimal formation, and that deviate in their degree of internal geophysical evolution that is driven by radiogenic heating. This suggests for the volatile accretion sequence to the inner solar system that it starts volatile depleted and then goes over to a dry sequence of accretion and ends with potentially volatile rich materials that are scattered inside. Now, for the last minutes of the talk, I want to switch actually for what this means potentially for the uniqueness or the distinction of the solar system structure and chemical composition relative to extrasolar planetary systems. So first of all, aluminum-26 itself is elevated 3 to 25 times relative to the galactic mean in the early solar system. This is a very active community. This is just a plot from one of my papers from a few years ago that shows predictions for the fractions of planetary systems in average star-forming regions, depending on the number of stars in these star-forming regions, and makes predictions for the prospective heating rate in extrasolar planetesimals. So the amount of aluminum-26, because of the short half-life and the necessary proximity to a nucleosynthesis event, suggests that there's strong variability in the initial aluminum-26 content. So what if this initial aluminum-26 content varies strongly by orders of magnitude across planetary systems? So we tested this a few years ago, and you know this type of plot already. This is planetesimal radius, this is aluminum-26 abundance relative to the solar system initial value. This is the solar system value planetesimals that are formed by the streaming instability typically are here. So what happens to exoplanetary statistics in terms of bulk water budget if they form by varyingly desiccating populations of planetesimals during accretion? So we tested this using a numerical model that includes planetary growth by planetesimal collisions, migration, and then the desiccation of these planetesimals during accretion by aluminum-26 heating. So assuming that planetesimals are of that size on average and have an order of magnitude lower aluminum-26 content than the solar system, then this is the resulting population statistically for G-type stars and for planets that are below 10 Earth masses. They're very water-rich. Their final bulk planet water mass fraction on average is comparable to the water mass fraction that is expected for the outer solar system or beyond the snow line, roughly on the order of 38%. Now, unsurprisingly from what I told you before, if you increase the amount of aluminum-26 heating, then the median of the distribution goes down. The solar system will like values approximately an order of magnitude below the one where no aluminum-26 is present, and even higher, of course, if that would be substantially higher than the solar system initial value. Now, these deviations on really a weight percent level bring us back to the very beginning, where I told you that actually Earth-like worlds and water worlds would be differing by high pressure ice phases at their surface. So is this measurable? Can we test this prediction using the exoplanet sensors? And our simulations suggest, yes, we can, with the extended test mission or in a few years with the Plato mission. This here gives this evidence or this testable prediction. It shows you the predicted mean radius deviation, the transit mean radius deviation of a population of planets that is either not heated by aluminum-26 or is heated like the solar system. So the zero here is the non-heated population. This is binned in planetary mass. And this line here are protoplanets that receive some water contribution, but that are heated with aluminum-26 like the solar system initial population. And this predicts that these planets are on average smaller than planets from planetary systems with no aluminum-26. So more aluminum-26, less water, smaller size. No aluminum-26, more water, larger size. Okay, so this is interesting in principle, and it makes the prediction that the initial bulk volatile content should strongly vary depending on the geophysical processing during accretion. But this is not everything, of course. There are a flurry of potential different geophysical processes that operate in the interior of planets and that can substantially alter both the structure and outgassing atmosphere of these worlds. This is shown what is here in this diagram, which basically shows you a wheel of time of planetary internal processes that impact the evolution of terrestrial worlds, starting from the planetesimal stage, going to the giant impact phase, magma ocean crystallization, and end with the secular geodynamic evolution of the planet. Now, the connection of planet formation and variability upward composition basically connect our understanding of planetary geophysics in the solar system with the exoplanet population. And it gives us a connection between the potential climates that we should expect for exoplanets with the processes that we can test in the solar system. Importantly, exoplanets have a detection sequence that actually starts with large masses close to their stars and then goes down, which is harder to detect, lower mass planets at wider orbits. And so this here shows a regime of potential planetary climates that is informed by the solar system, showing installation and planetary mass. The Earth is about here. Because of the sensitivity of transit and radial velocity surveys, we start to probe here. And this enables us to probe actually these high temperature regimes of early planetary evolution that we do not have access to at present day in the solar system. This is important because different initial composition bulk budgets, for instance, predict that the cooling timescales of planets from their initial liquid and vapor state, depending on their atmospheric quantities of certain key species, such as water vapor, hydrogen, CO2, etc., should differ substantially. This is shown in this plot, going from very high temperatures in the magma ocean stage to colder solidified states when the planets basically have cooled down. You see that depending on the atmospheric composition for different types of absorbers, the heat flux of these atmospheres is substantially different, predicting a variety of different evolutionary pathways. And this is, I have only 2 slides left, so I will stop in a few minutes. This is why a few months ago, 2 or 3 months ago, we tested what would be the impact of actually having molten planets among the extrasolar planet census relative to the standard assumption that all planets that we measure, and what I showed you in the very beginning, are solid. So this here is the standard structure model that is used in the exoplanet community, where it is used that where it is assumed that planets that we measure typically are solid, with a solid core, a solid mantle, and all volatiles being in the atmospheric reservoir. We compared this by assuming that parts of this interior could be molten according to the equations of state that we have from high pressure experiments, and a model where the interiors can be molten, but additionally, actually, the water component in these planets can partition in the interior, which is the more realistic case because water is very soluble in silicate melts. And so comparing these 3 cases, we found that actually comparing the dry magma ocean versus the wet magma ocean case, the water mass fraction for a given initial water mass fraction of the planet, different masses of these planets, the radius deviation from a dry to wet magma ocean reaches up to 16%. And for a solid versus the wet magma ocean case, the radius deviation for these types of initial conditions and assumptions is still 8%. Again, on a testable difference with current radial velocity in transit surveys. Now for the turning this around, for the typical situation in an exoplanet inference, where you know your planetary radius, you know your planetary mass from the radial velocity measurement, this predicts that the inferred water mass fraction and weight of that specific planet can differ by up to 1 order of magnitude, which is dramatic. To illustrate this, what kind of consequences this can have, this is the very last plot I'm showing. This is the planetary radius again in Earth radii, and this is the planetary mass. Ignore all these dots here, but let's focus just on 55 Cancri. This is a very well-known super Earth that is discussed frequently in the community because it orbits one of the brightest stars that we can actually observe. And these lines here basically are the comparison of these different qualitative types of interior models with a weight percent of 5.4. And you see already that if you vary this fraction, then 55 Cancri E can be explained with substantially different water inventories. Specifically, our inference here for this very famous planet suggests that contrary to previous assumptions, the amount of water in its interior, which is typically assumed to be completely dry but molten, can reach up to several weight percent of water with a 0.1 weight percent steam atmosphere on top. And this suggests that previous calculations of atmospheric loss substantially overestimated the amount of loss of volatiles that can be lost, because they did not account for volatile locking in the planetary interior. And with that, I just want to shortly summarize my talk. So I basically said that the solar system dichotomy, the structure and chemical segregation in the solar system that we see, can be explained by the heterogeneous mode and timescale of accretion and geophysical evolution that is driven by aluminum-26 heating. This suggests that exoplanet climates should show a large diversity across planetary systems because atmophile elements are fractionated from the internal evolution during accretion. And we can use hot rocky exoplanets as probes of the evolutionary pathways, but that requires a much more advanced coupled climate interior models to serve as blueprints for exoplanet observations and help us to characterize the climate and surface state of terrestrial and rocky worlds. And with that, I am done. Thank you so much for your attention.
Thank you, Tim. Great talk. I see Bruce has typed a question in the chat. Tim.
Yeah, maybe I should read it so that everyone Okay, so if I understand things correctly, the snow line is at 1 AU, about 0.2 mega-year after CAI formation. In that case, where did CAI formation occur, I guess, which requires temperatures above 1000 Kelvin take place? And if it was in the inner solar nebula, what then made that region of the disk cold again? Or if CAI came from the outer regions, what made that region hot while the inner region was cold? Yeah, so our paper is not focused on CAI formation, but is perfectly consistent with CAI formation and with the first scenario that you're basically suggesting there. Let me go back to that. So yeah, this is a good plot here. So CAIs in this scenario would form close to the sun, and the material, there is a outward transport of solid materials during the class 1 stage. We are not the first one, so we didn't make a huge point out of this. Multiple authors have already shown that by zonal flows in the inner disk, the material that is initially accreted onto the sun, protosun, and heated strongly in the inner disk can be transported outward, where it then would be incorporated in the CC population of the outer solar system like we see it today. You can actually see this quantitatively. Let me find the plot. Here in this plot, here, this is the, let's focus on, for instance, the red lines. This is the Pebble Flux at 2 AU. You see that in the very early phase, for 400,000 years, for instance, the total flux is dominated by outward flux. This could be CAIs. Did that answer your question?
Not exactly, because I thought at this point in time, if I understand the time scale on the bottom graph you're showing, if that also applies to the top graph A, I thought at that point in time after CAI formation, you had the snow line at about that position. Or am I misunderstanding that? I don't understand how you're making a CAI in a region of the nebula where you have the snow line at that time.
So at 0.4 mega years, the snow line is at 7 AU. CAIs form in a 200,000 year time window. And if let's look at this left side plot, they would form somewhere here or inside even on that point, where temperatures are really high, very early, very brief time episode.
Okay, we could talk about it later. It seemed to me the time when you had your high flux was still a cold time, but thank you.
Oh, no, it's very hot. Actually, seriously, this is not a new invention. There's multiple papers, for instance, I think one of that is completely compatible with this model. They use the exact same model, actually. Yang and Chiesla, 2012 in MAPS. They basically used very, very similar model than we do here to analyze their simulation specifically for the CAI storage problem. They basically, so our simulations are completely consistent with their estimates from 10 years ago now. Can you explain the mechanism of the streaming instability? One might naively expect viscous drag to relax the particle velocity to the gas velocity. Yes, so the streaming instability basically works like swarms of birds or the peloton in bike races. So once you have if you generate any overdensity in the disk, for instance, via a dense region in the gas distribution, then some of those particles will actually settle in there. And the particles that drift into that region, they experience less headwind because they are shielded from the particles that are already present in that region. And that leads to an accelerated drift of particles into that region because they can orbit with the Keplerian velocity at that specific orbit. And that is a runaway process that leads ultimately to gravitational collapse. I thought previously the isotopic dichotomy is due to Jupiter blocking the exchange of material. Any comments on Jupiter's role? Yes, our paper was an answer to the Hoyer 2017 paper presenting an alternative mechanism to generate the isotopic dichotomy, not related to the presence of Jupiter, and therefore questioning the inference in the decretion timescale of Jupiter. We basically alternatively suggest that actually the mechanism that ultimately generated the formation of Jupiter already generated the isotopic dichotomy imprinted into the initial planetesimal population. Should I just go down the line? Is that fine, Jeff?
Yeah, we can go on to Bill next. Yep.
Yeah, so I was going to add something similar to Kuhn, so let me follow on. So reservoir 2, like in this image we see here, let me thank you also, by the way, for the excellent talk. It doesn't require Jupiter, but since you're locking up the material in planetesimals, implicitly, as long as, well, any giant planets could form. So my question is, where is Jupiter in this story? I see the ice line, planetesimal formation, ice line is out beyond, it's almost at 15 AU and then moves back in. Should we impute that the ice giants form in, or that Jupiter formed farther out and basically migrated in with the ice line?
Yes. So the simulation doesn't go there. We do not form Jupiter explicitly in the simulation.
I understand that, but you must have thought about it, that's all.
Exactly, yes. So Jupiter would probably form somewhere here, much later. And this would have indeed an effect actually on the subsequent growth of this reservoir. This would change things. And of course, that is something that we have to do in the future. Now, I think there are two things to say about this. The seemingly notion in the community that it's already proven that this worked like via Jupiter blockage. This is a hypothesis that has been qualitatively suggested, and there have been actually no quantitative simulations that show that. Whereas our model, in this specific plot on the right-hand side, demonstrates quantitatively that there's a shift in Pebble Flux in the inner and outer solar system just by the establishment of these different reservoirs. And so this operates in the timescales where we have evidence for this isotopic dichotomy. This sort of decouples the growth of Jupiter itself from the isotopic dichotomy itself.
Thank you.
This is Katrina Lodder speaking.
Hello.
Hello, interesting talk. My question is, you have the traffic jam which requires the presence of dust. And in order to get a streaming instability, you need a higher dust to gas ratio. However, isn't that somewhat a circular reasoning, because you have to have dust to begin with, which you have a problem making? You mentioned that it's very difficult to make the dust. So if you need a higher dust to gas ratio to enable to further dust formation, so how do you get the dust to begin with? I think there's a circularity in there that are trying to figure out how you get out of that.
Yeah, maybe I didn't explain this well enough. Sorry for that. You don't need to have an enhanced dust to gas ratio in order to make dust. You just needed to jump the centimeter barrier. Let me go back to that specific last slide. So if you go from micrometer to millimeter, this is fine. And sticking experiments indicate that specifically if you have an ice contribution that makes potentially the dust stickier, then you can definitely grow to millimeter, potentially centimeter sizes in some areas. But you just can't grow further, because anything above that, one slide before actually than that, here at the bottom, the dust starts bouncing and fragmenting and drifting very rapidly. And so the streaming instability basically solves this growth barrier from millimeter to kilometer sizes by collecting dust of millimeter sizes in locally active regions in the disk. And this traffic jam at the snow line sort of acts like a honeypot for the dust particles. So they can grow on the outside of the disk until centimeter sizes roughly, but they then can't grow further. This size already, they drift rapidly inside. And so they will basically drift toward this overdense region at the snow line and then just be stuck there because of this minimization of the headwind at this location, because some grains are already there. And this ultimately is a runaway process and triggers planetesimal formation. So I don't think there's a circular argument there, actually.
Okay, may I follow up on that? So this also indicates that you have still an efficient mixing mechanism of millimeter-sized particles, right?
Well,
and what I'm wondering about that, how do you actually preserve, if you assume, well, the problem is how do you have so isotopically heterogeneity to begin with, and how do you preserve it if you still have bringing together the millimeter-sized dust in the
so
the dichotomy?
Yeah, so the dichotomy, and I mean, we have to be careful with what we call a dichotomy, right? So this is on the epsilon scale. So 1 to 10 parts per one part to 10,000. So it's actually a very small dichotomy that required much better measurements 10 years ago than we had to access to before. And so on a first and second order, the solar system is homogeneous, but it's not exactly homogeneous, right? And so some mixing is absolutely permitted and probably necessary, because if you just compare the isotope fractionation from two different types of nucleosynthesis events, this is much stronger than the fractionation that we see here in this plot. And so you need some mixing actually to explain this homogenization, but you just cannot have complete mixing. And so what we're basically arguing here is that this preservation of an initial signature from two populations that are building up preserves the right amount of initial isotope fractionation. Compare that with the Jupiter argument makes no such quantification of the problem. They're just saying there's a block in the disk, and that explains the dichotomy, without any calculation actually to which degree the dust population is actually kept heterogeneous. So I think we have to work on this problem still, and this absolutely doesn't solve all the problems, but it is a way to keep heterogeneity in the disk. If the initial disk is heterogeneous, and it was, because this is what the isotopic fractionation indicates.
All right, we'll give Lee, I think, the last question of the day.
Thank you, Tim, for a wonderful talk. I just want to make sure I understand the reason aluminum 26 is nailed for this differentiation and heating mechanism. That it is unique in that it is produced with sufficient abundance and has the half-life required 1,000,000 years, and there is nothing else in the chart with those two qualities.
Exactly.
And the magnesium maybe 26 enhancement, but that's a post facto maybe association. But the principal physical arguments are that it's light enough to be produced in large abundance, and its lifetime is consistent with the planet evolutionary timescales.
Yes.
Early planetary.
The magnesium
and it's unique in that quality, those two qualities.
Both right. The magnesium, by the way, is the evidence for aluminum 26. It's a decay product. And so
right, but that's a supportive argument. But if you went to, you could not find another isotope. I mean, forget the evidence for magnesium-26. You cannot find another isotope produced with sufficient quantity and lifetime suitable in nucleosynthesis. It's the only candidate. Is that correct?
For heating, you mean?
For heating, yes.
Well,
providing its non-neutrino energy, which is probably about 1.2 MeV per decay or something.
1.4 or something. Yeah. Well, for a long time.
Is that true? Is that true?
Yes. But let me shortly give you more detail. For a long time, the community has discussed also iron-60 as a potential heat source, which is why it's on this plot.
But it's too heavy.
Yes, and multiple. There's enough. I guess the community has converged in the past few years on the view that there's not enough iron-60 for acting as a general heat source. That brings a problem with it, by the way, because it suggests that actually the aluminum cannot be produced by supernovae, at least not according to our standard nucleosynthesis models. It also cannot be produced by spallation, so it's probably Wolf-Rayet star, something like that. But the debate is open.
Thank you.
All right. Well, I want to thank you one last time, Tim. It was great to hear a model where we don't need Jupiter to keep isotopic differences between the inner and outer solar system. So it's a neat paradigm change for explaining the data that we see between carbonaceous chondrites and inner solar system materials.
Thank you so much.
Thank you. Well, have a great evening. And on behalf of WashU and the Physics Search Committee, thank you very much for today.
Thank you, everyone. Thank you for the great discussions, and have a good day then. See you. Bye.
Bye-bye.
Thank you again, Tim.